Tonight we're going to do something slightly dangerous to your sense of importance. We're going to take the world you live on, the one that feels impossibly huge, and make it almost disappear. Not with special effects, just with honest numbers and a relentless zoom out. By the end of this journey, Earth will feel smaller than you ever imagined, and that feeling will quietly stay with you. That discomfort is not a bug, it is the point, because it changes how you see everything else in your life. If you enjoy having your perspective stretched like this, tap like, subscribe, and let us start shrinking our home together. Let us begin where every human story begins, standing on solid ground. From down here, Earth feels enormous. You can live an entire life, work, love, travel, raise a family, and still never see more than a thin slice of this planet. A road trip across a continent feels epic. A long flight across an ocean feels like crossing the world. Your body learns a very local lesson, which is that Earth is big and you are small. That lesson is true on a human scale, and completely misleading on a cosmic one. Think about the surface you're standing on. Earth has a diameter of a little under 8,000 miles at the equator. That gives it a circumference of about 25,000 miles. Imagine you could walk that entire circle around the equator on a magical, perfectly safe path over the ocean. If you walked at about 3 miles per hour for 8 hours every day, you would need roughly 3 years and an extra month to get back to where you started. 3 birthdays of nothing but horizon and waves. That is a serious commitment just to complete 1 lap. Now stretch that idea vertically. The tallest mountain on Earth, Mount Everest, rises to nearly 30,000 feet above sea level. For early humans with no airplanes and no satellites, that was a wall at the edge of what felt possible. Below them, the oceans reach depths that swallow skyscrapers. The Pacific alone covers an area so vast that early explorers could sail for months and see nothing but water and sky. If you only have your feet, your eyes, and maybe a boat, this planet feels effectively infinite. We can put a number on that infinity feeling. The total surface area of Earth is about 197 million square miles. That includes land and ocean. Imagine you had a very strange mission. You must visit every single square mile of the planet and spend exactly 1 second in each one. No breaks, no sleep, no snacks, just teleporting from one patch to the next. Even at that ridiculous pace, you would be traveling for more than 6 years without stopping. Your entire life would compress into an endless slideshow of new terrain, and you would still be experiencing Earth at the resolution of a single second per square mile. To make that more concrete, take the United States, one of the largest countries on the planet. It covers about 3.88 million square miles. That sounds enormous until you compare it to the whole world. It turns out to be less than 2% of Earth's surface. All the cities, highways, farms, deserts, and forests inside that border fit into a tiny slice of the global pie. When you see a map with your country filling the screen, your brain quietly lies to you. It forgets everything that is not drawn. You can see why early humans thought Earth might be flat and basically infinite. When you look toward the horizon, it really does look flat. The curvature is too subtle to notice from the ground. You can walk for days, and the horizon always stays the same distance away. The sky above looks like a dome with small lights pinned to it. The ground beneath you looks like it could continue forever in all directions. With no way to leave the surface, the idea that Earth was everything was not arrogance. It was just common sense. Only when humans started climbing higher did that sense of endless flatness begin to crack. From a tall mountain, you can just barely hint at the curve. From an airplane, you can sense it more clearly, the horizon bending gently downward at the edges of your field of view. From orbit, the argument is over. Astronauts see the limb of Earth as a clean arc, a glowing blue circle wrapped in a thin, fragile atmosphere. The planet that once felt infinite fits inside a single photograph. For the first time, our brains had to accept a new idea. Earth is not everywhere. It is something, floating in a much larger nothing. That image of a glowing marble in black space is already a kind of insult to our old instincts. It takes everything you ever knew and compresses it into a small circle surrounded by emptiness. Yet even that picture is still lying to you in a quiet way. When we see Earth alone, centered in the frame, it still looks huge. The camera gives it respect. There is nothing else in the shot to challenge it. Your brain thinks, yes, it is a ball, but it is a very big ball. We have not broken the illusion yet. We have just changed its shape. To really understand how small Earth is, we have to stop treating it as the default reference size and start treating it as one object among many. That means changing the question from how big is Earth to how big is Earth compared to everything else that is out there. As soon as we do that, the numbers you heard earlier start to behave differently. 25,000 miles around the equator sounded huge when it was just you walking. When we lay that circle next to the scale of the solar system and beyond, it becomes a rounding error. Before we zoom all the way out, there is one more shift in thinking we need to make. Our senses are built to understand hills, cities, and weather, not galaxies and voids. You're naturally impressed by the size of a country, but numb to the difference between millions, billions, and trillions. That is not a personal flaw. It is an evolutionary compromise. Your ancestors survived by noticing the movement of a predator in the bushes, not by estimating the distance to the nearest star. So throughout this journey, your brain is going to try to downplay the scale we're talking about. It will quietly translate mind-bending numbers into something that feels manageable. You will need to catch it doing that, so we start gently. First, we will take Earth and compare it to the closest things we can reach with spacecraft and calculations, the Moon and the Sun. We will keep the numbers simple and the mental pictures clear. We will see how far you really have to travel to leave Earth behind, and how quickly our planet stops being the main character once other objects enter the frame. Right now, in your mind, Earth is still the star of the show. In the next part, as we step outward to our nearest neighbour and our parent star, that confidence begins to crack. We start our first zoom out with something familiar. The Moon. It feels close. You can point at it with your finger. It hangs in the same sky that you walk under every night. From the ground, the Moon looks like it is just past the clouds, a glowing disk you could almost reach if you stacked enough mountains. Your instincts whisper that Earth and the Moon live in the same neighbourhood, almost touching. Reality is not impressed by those instincts. The Moon orbits Earth at an average distance of about 239,000 miles. That number is already beyond anything you will ever travel in your life. To get a feeling for it, imagine driving at highway speed around Earth's equator once. Now imagine doing that not once, but about 9.5 times without stopping. That total distance is roughly the empty space between you and that pale light in the night sky. For the Apollo astronauts, even in a rocket riding a pillar of fire, it took about 3 days to cross that gap. Now compare sizes. Earth is nearly 8,000 miles wide. The Moon is a bit over 2,100 miles across. That makes the Moon about 27% of Earth's diameter. If Earth were a basketball sitting on the floor, the Moon would be a tennis ball, not a marble, not a speck. A real companion. And here is the key twist. In that basketball and tennis ball model, you do not put the balls almost touching. You place the tennis ball about 30 basketball widths away. That is how much empty space really sits between Earth and the Moon. Most diagrams lie about this. Textbook illustrations squeeze the Earth and Moon together in the same panel, so you can see both objects clearly. That makes the distance look small and cozy. In reality, you could line up about 30 Earths in a row between the two worlds and still have a bit of room to spare. Our closest neighbour lives across a gulf of almost pure nothing. This is the first hint that space does not care about comfort. It cares about ratio. Objects are tiny. The distances between them are huge. The Earth-Moon pairing is also special. Most planets keep tiny moons as playthings. Mars has 2 misshapen rocks. Many moons around the giant planets are little more than captured debris. By contrast, our Moon is big enough that astronomers sometimes call Earth and the Moon a double planet system. That oversized companion has shaped your life in ways you almost never notice. Every day, the Moon pulls on the oceans and creates tides. That constant sloshing of water has been sculpting coastlines for billions of years. It may have helped early life move from tide pools onto land. The Moon's gravity also grabs Earth's tilt and holds it steady. Without that grip, Earth's axis would probably wobble wildly over long timescales. The result would be extreme climate swings, ice ages that lock the planet down for ages, heat waves that boil away habitability, complex life, and certainly human civilization might never have had a stable stage to evolve on. There is another beautiful accident in the Earth-Moon-Sun geometry. In our sky, the Moon and the Sun appear almost exactly the same size. The Sun is about 400 times wider than the Moon, but it is also about 400 times farther away. Those two ratios nearly cancel each other out. The result is the total solar eclipse, those rare moments when the Moon slides in front of the Sun and covers it perfectly, revealing a ghostly corona. Nothing in physics required this to happen. It is just a coincidence in timing and distance. Over millions of years, the Moon is slowly spiraling away from Earth, drifting outward by about 1.5 inches every year. In the far future, it will look too small to produce a perfect eclipse. We live in a thin slice of time when the alignment works out. Already you can feel Earth shrinking. The planet that once filled your entire world is now part of a two-body system, where the gap between the bodies is much larger than the bodies themselves, yet we're still very local. We have not even acknowledged the real ruler of this neighborhood. Turn now to the Sun. Everything you have ever done has happened inside its light. It warms your skin, drives your weather, powers your food chain. Without the Sun, Earth would be a frozen rock wandering in darkness. From 93 million miles away, the Sun looks like a bright coin in the sky. Put it next to Earth on the same scale and the story changes. The Sun has a diameter of about 864,000 miles. That is roughly 109 times wider than Earth. If you lined up Earth side by side, you would need more than 100 to span the face of the Sun. Volume is even more dramatic. You could fit about 1.3 million Earth-sized spheres inside the volume of the Sun if you packed them efficiently. Every continent, every ocean, every city, every person, all of human history, all of it took place on a world that could be swallowed 1,300,000 times by the star we orbit. The Sun also owns almost all the mass in the solar system. About 99.86% of everything that has weight in our system sits inside that glowing ball. All the planets, moons, asteroids and comets combined make up the remaining tiny fraction. When you think of our system as the Sun and some dust, you're not being rude, you're being accurate. Earth is a speck in the leftovers. Even the distance between Earth and the Sun is a kind of insult to your sense of size. 93 million miles is our average orbital distance. Astronomers call it 1 astronomical unit. Light, the fastest thing in the universe, takes about 8 minutes and 20 seconds to cross that space. When you look at the Sun, you're seeing it as it was 8 minutes ago. If the Sun magically disappeared, you would still feel its light and warmth for over 8 minutes before reality caught up. For a car at highway speeds, this same trip would take on the order of 176 years of non-stop driving. The fastest spacecraft humans have launched need months to dive inward, even when they are slingshotting around planets and falling almost straight down the Sun's gravity well. Parker Solar Probe, which has reached speeds over 400,000 miles per hour near the Sun, still crawled there compared to light. Your everyday sense of fast and slow has no meaning here. Despite the way it dominates our sky, the Sun is not a special monster on a galactic scale. It is a G-type main sequence star, often called a yellow dwarf. Middle-aged, about 4.5 billion years old, quietly converting hydrogen into helium in its core. Every second it fuses roughly 600 million tons of hydrogen. A small part of that mass turns into energy through nuclear fusion and floods the solar system with light. In 1 second, the Sun releases more energy than human civilization has used in its entire history. The surface of the Sun simmers at around 10,000 degrees Fahrenheit. Deeper inside, near the core, the temperatures climb to tens of millions of degrees. The pressure there is hundreds of billions of times the air pressure at Earth's surface. Under those conditions, nuclei that would normally repel each other are forced together. That fusion is what keeps the Sun shining and what makes Earth anything other than a frozen sphere. Sometimes the Sun reminds us that it is not just a gentle heat lamp, Solar flares and coronal mass ejections hurl huge clouds of charged particles into space. When one of those clouds slams into Earth's magnetic field, it can light up the polar skies with auroras. It can also disturb satellites, mess with radio communication, and in extreme cases threaten power grids. Earth is not in charge here. We are passengers inside a moving halo of magnetic protection around a turbulent star. This is the first big lesson in cosmic humility. The place that feels like everything is actually a small, temperate surface on a small rocky world. That world is locked in a gravitational relationship with a moon that sculpts its tides and steadies its tilt. Both of them orbit a star so large that Earth becomes an afterthought in its statistics. When you hold those three objects in your mind together, Earth finally loses its illusion of being the default size of reality. In the next part, we will zoom out again and meet the rest of the planets, the asteroid belt and the icy outskirts of our system, and we will watch our little world shrink even further into the background. We have met the moon and the sun. That alone was enough to knock Earth off its throne. Now it is time to reveal the rest of the stage this star rules. When most people picture the solar system, they imagine a tidy row of planets, evenly spaced like beads on a string. The real layout is much stranger. 4 small rocky worlds huddle close to the sun. Then comes a vast gap filled with scattered rubble. Beyond that, 4 giant planets dominate, followed by a distant halo of frozen leftovers. Earth is just one rock in that architecture. Closest to the sun is Mercury, a scorched and battered world. Mercury is a little over 3,000 miles wide, less than half Earth's diameter. Its surface is covered in craters because it has almost no atmosphere to burn up incoming rocks. With no air to trap heat, its temperatures swing violently. On the day side, the surface can reach around 800 degrees Fahrenheit. On the night side, it can plummet to roughly minus 290 degrees. That is a range of more than 1,000 degrees between noon and midnight. Mercury also plays weird games with time. It takes 88 Earth days to orbit the Sun, but it spins so slowly that one sunrise to the next lasts 176 Earth days. On Mercury, a day is longer than a year. If you lived there, you could watch the Sun crawl across the sky for months. Compared to that, Earth's 24-hour spin and relatively gentle climate feel almost unnaturally kind. Next out is Venus, which people once called Earth's twin. It is only slightly smaller than Earth, with a diameter about 95% of ours. If you just compared size, you would think the two worlds must be similar. They are not. Venus is wrapped in an atmosphere made mostly of carbon dioxide with clouds of sulfuric acid. The air at the surface is about 90 times denser than Earth's air. Standing there would feel like standing almost 3,000 feet underwater on Earth. All that thick gas traps heat with a runaway greenhouse effect. Surface temperatures on Venus hover around 900 degrees Fahrenheit, hot enough to melt lead. It is even hotter than Mercury, despite being farther from the Sun. Venus also rotates backward compared to most planets, and spins so slowly that a single day there lasts longer than its year. Venus shows us what happens when a planet similar in size to Earth takes a different atmospheric path. Same basic dimensions, completely different fate. Then there is Mars, smaller than Earth but far more familiar. Mars is about half Earth's diameter. It has polar ice caps made of water ice and frozen carbon dioxide, weather, dust storms, and ancient river channels carved by water that once flowed on the surface. But something went wrong here. Mars lost most of its atmosphere. Early Mars probably had a magnetic field like Earth's. That field shields us from the constant stream of charged particles flowing from the Sun, called the solar wind. On Mars, the core cooled and the magnetic field faded. Without that protective bubble, the solar wind slowly stripped away the Martian atmosphere over hundreds of millions of years. Today, the air pressure at the surface is less than 1% of Earth's. Liquid water cannot remain stable. It either freezes or boils away. Average temperatures sit around minus 80 degrees Fahrenheit. Whatever might have happened there, Earth ended up as the warm, stable middle child in a family of extremes. Between Mars and the next large planet lies a strange region, the asteroid belt. Popular culture shows it as a crowded maze of tumbling rocks that spacecraft must dodge. Reality is more empty. The belt contains millions of rocky objects, but they are spread across such a large volume that a spaceship could pass through without ever seeing one. The total mass of the entire belt is less than a small fraction of our moon's mass. The largest object here, Ceres, is a dwarf planet about 588 miles across, roughly the width of the state of Texas. Spacecraft that orbited Ceres found hints of a subsurface ocean and salts shining on its surface. It is a reminder that even small bodies can hold surprises. But from a distance, the belt is not a wall. It is a sparse scattering of debris in a vast ring of nothing. The emptiness between objects is once again much larger than the objects themselves. Past that emptiness, the solar system changes scale. Jupiter waits. With a diameter of about 86,881 miles, Jupiter is roughly 11 times wider than Earth. In terms of volume, more than 1,300 Earths could fit inside. It holds more mass than all the other planets combined. If you think of the planets as a family, Jupiter is the heavyweight that sets the tone. Jupiter also acts like a cosmic shield. Its gravity pulls in or deflects many comets and asteroids that might otherwise wander into the inner system. Some scientists think this may have reduced the number of catastrophic impacts on Earth, buying time for complex life to evolve. Its most famous feature, the Great Red Spot, is a storm larger than Earth itself that has been raging for centuries, with winds around 400 miles per hour circling its edge. Imagine a hurricane that could swallow our entire planet, and you are in the right ballpark. Next is Saturn, almost as wide as Jupiter but less dense. Saturn is about 72,367 miles in diameter and could hold more than 700 Earths by volume. Yet its most iconic feature is not its bulk, it is the ring system. Those rings stretch tens of thousands of miles from the planet, but in most places are only about 30 feet thick. If Saturn were the size of a basketball, its rings would be thinner than a sheet of paper. From a distance, they look solid. Up close, they are made of countless particles of ice and rock, ranging from grains to boulders. Saturn carries a swarm of moons as well, including Titan, larger than the planet Mercury, with a thick nitrogen atmosphere and lakes of liquid methane and ethane on its surface. Wherever you point around these giants, you find structures that dwarf Earth. Farther out still, the ice giants Uranus and Neptune circle in the cold. Uranus has a diameter of about 31,518 miles. Neptune is slightly smaller, at around 30,599 miles. Each could fit dozens of Earths inside if you counted by volume. Both are blue worlds rich in methane, with deep atmospheres and possibly strange exotic forms of ice under crushing pressures. Uranus is tilted dramatically. Its axis lies almost in the plane of its orbit, so it essentially rolls around the Sun on its side. That tilt is about 98 degrees from vertical. As a result, each pole can spend over 40 years in continuous daylight, followed by over 40 years in darkness. Neptune, the most distant main planet, takes about 165 Earth years to complete a single orbit. Its wind speeds can reach around 1,200 miles per hour, the fastest measured in the solar system. These outer worlds are remote, huge, and utterly unlike anything you experience on Earth. Beyond Neptune, the picture shifts again. The Kuiper Belt stretches outward for billions of miles. It is a region of icy bodies left over from the early days of planet formation. Pluto lives here, along with other dwarf planets. Pluto is about 1,473 miles across, so you could line up a little more than 5 Plutos across Earth's diameter. New Horizons, the spacecraft that flew past Pluto, revealed mountains of water ice, plains of frozen nitrogen, and a thin extended atmosphere. Pluto stopped being the 9th planet, but it did not stop being interesting. Even the Kuiper Belt is not the true outer boundary. Far beyond, starting around 2,000 times farther from the Sun than Earth, a vast sphere of icy objects is thought to surround the solar system. This is the Oort cloud. It probably extends out to nearly 2 light-years from the Sun, almost halfway to the nearest star. No one has seen an Oort cloud object directly, We infer its existence because long-period comets seem to fall inward from that distant shell when their orbits are disturbed by passing stars or tides from the galaxy itself. If you imagine the solar system drawn to scale, the shock really lands. Picture the sun as a basketball. On that scale, Earth is a peppercorn about 26 feet away. Neptune would orbit roughly the length of a football field from the sun. The Kuiper belt lies beyond the stadium. The hypothetical Oort cloud would be a faint bubble extending for miles around your tiny ball of light. Earth's entire orbit would be a tight ring near the center, almost invisible compared to the size of the whole structure. So when we say the solar system is big, we are underselling it. It stretches for trillions of miles in every direction. Most of that volume is empty space with the occasional world or chunk of ice drifting inside it. Earth occupies one thin shell in that enormous bubble, 8,000 miles across, circling 93 million miles from the Sun, deep inside what is essentially the inner core of our local system. Already, on this first step outward, our planet has gone from everything to almost nothing. And yet, from the perspective of the galaxy, we have barely taken a step. In the next part, we will leave this vast but local neighborhood entirely and head out toward the nearest stars. There, the distances grow so enormous that the entire solar system collapses into a single point of light, and Earth vanishes from the map altogether. Leaving the solar system is less like stepping over a fence and more like walking off the edge of a continent into a black ocean that never ends. Beyond the Oort cloud, there are no more planets, no more belts, no more tidy labels on a classroom poster. There is just interstellar space, the thin medium between stars. This is where our sense of distance finally snaps. To survive it, we need a new unit. That unit is the light year. A light year is not a time, it is a distance. It is the distance that light travels in 1 year as it moves along at about 186,000 miles every second. Multiply that speed by all the seconds in a year, and you get a number so large it becomes abstract. 1 light year is about 5.88 trillion miles. Trillion with a T. Even saying it out loud does not make it easier to picture. The distance from Earth to the Sun, our comfortable 93 million miles, suddenly looks tiny next to that. If the Earth-Sun distance is 1 unit, 1 astronomical unit, then the nearest star is more than 260,000 of those units away. Imagine the distance between Earth and the Sun as a single step on a long walk. The nearest star would be more than 260,000 steps away. That is the difference between walking across a room and walking across a country. So who owns that first light year out from us? The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system. It sits about 4.24 light years away. In miles, that is roughly 25 trillion. Written out, that is 25 followed by 12 zeros. Every number we have used so far, every planetary orbit and solar system diagram, fits into a tiny corner of the space between us and that one star. Here is another way to feel it. Remember that the Sun is 93 million miles away. Proxima Centauri is about 268,000 times farther. If the distance from Earth to the Sun were shrunk down to 1 inch, then Proxima Centauri would be about 4 miles away. You would hold a tiny model of our orbit between 2 fingers, then have to drive across town to reach the nearest star. Humanity has actually launched something into this interstellar gulf. Voyager 1, the little spacecraft that flew past Jupiter and Saturn, left Earth in 1977. It has been travelling outward for more than 47 years. Right now it sits about 15 billion miles from Earth, moving at roughly 38,000 miles per hour relative to the Sun. That sounds impossibly fast in human terms, faster than any plane, faster than any bullet. At that speed, how long would it take Voyager 1 to reach Proxima Centauri if it were heading that way? The answer is about 73,000 years. Entire human civilizations rise and fall in a few thousand years. Voyager would need more than 10 times that just to reach the nearest star. And the funniest part is that it is not even aimed in that direction. It is heading out along its own path, a tiny messenger that will drift for ages through empty space. Even if we dream bigger and imagine a future spacecraft that can travel at 10% of light speed, we still run into the wall of distance. 10% of light speed is tens of thousands of miles every second, far beyond anything we can currently build. At that speed, the trip to Proxima Centauri would still take more than 40 years. You could launch as a young adult and arrive as an older person, having spent your entire life inside a vessel, crossing a darkness where nothing much changes. From the vantage point of Proxima Centauri, the entire solar system collapses into a single unresolved point of light. Even powerful telescopes would see our sun as one bright star among many. Earth would be hopelessly lost in that glare, too close and too faint to pick out. There would be no image where you could zoom in and point at a pixel and say, there it is. Our planet would not just be small, it would be gone. Now that we have used Proxima Centauri as a measuring stick, let us look at the star itself. Proxima is a red dwarf, the most common type of star in the galaxy. It is much smaller and cooler than the Sun. Its diameter is only about 129,000 miles or so, roughly 14% of the Sun's diameter. Around 8.5 Earths could line up across its face. It has around 12% of the Sun's mass, and shines much more dimly. Because Proxima is so small and cool, it sips its fuel rather than chugging it. Red dwarfs burn hydrogen incredibly slowly. The Sun will last for about 10 billion years in total as a normal star. Many red dwarfs will keep shining for trillions of years. The universe is only about 13.8 billion years old. That means no red dwarf has ever died of old age. Every red dwarf that has ever formed is still out there, quietly glowing. Proxima is not entirely quiet though. It is a flare star, prone to sudden eruptions. It can throw off powerful bursts of radiation that dramatically brighten it for short periods. That kind of violence is bad news for planets hugging close to stay warm. The radiation from a strong flare could strip away an atmosphere or sterilize a surface. Even so, we know Proxima Centauri has at least 2 planets. One of them, Proxima Centauri b, orbits in the star's habitable zone where liquid water could exist on a planetary surface. On paper, that sounds promising. In practice, that world is likely locked into a tidal embrace, with one face always pointing toward the star, one face always in darkness, and frequent flares sweeping over it. Life there, if it exists at all, would have a difficult time. Still, it is striking that the nearest star to us is not just a bare lamp in the dark, it has worlds. Proxima does not float alone. It is part of a triple system with Alpha Centauri A and Alpha Centauri b, 2 sun-like stars that orbit each other farther out. All 3 are gravitationally bound. This triple system is our true closest stellar neighbour, a miniature family of stars sitting a few light years away across the void. For generations, science fiction has imagined ships bound for Alpha Centauri. In reality, we do not have anything close to the technology needed to send humans there on a reasonable timescale. And beyond that, Proxima Centauri is just the first stepping stone. The next nearest star is Barnard's star about 6 light years away. Sirius, the brightest star in our night sky, sits at around 8.6 light years. Those distances might sound similar, but every extra light year is another 5.88 trillion miles added to your journey. Move beyond the local handful, and the numbers become even more surreal. Betelgeuse, the famous red supergiant in Orion, is roughly 700 light years away. When you look at Betelgeuse tonight, you are seeing light that left that star around the time the Crusades were ending on Earth. It has been travelling non-stop through space during the entire span of documented human history since then, just to land on your eyes for a fraction of a second. This is one of the quiet miracles of starlight. The night sky is not just a map of positions, it is a map of times. Every point of light is a message from a different era. Nearer stars are sending you relatively recent news. Distant ones are showing you their ancient past. Your sky is a time-layered photograph of the galaxy that your brain compresses into a single moment for convenience. By now, Earth has completely vanished from the story. The solar system itself is no longer something with structure. It is a bright dot surrounded by darkness, moving slowly among other dots. To talk about our real home at this scale, we have to give up on planets entirely and start thinking in terms of star fields. Our next step is to pull back even farther and see how all these stars are arranged, to place the Sun inside the enormous spiral city of the Milky Way. When we do that, even our star stops feeling special. Up to now, we have been playing in one tiny corner of reality. A star here, a nearby star there, a few light years between them. Impressive, but still local. It is time to admit something unsettling. Every single star you have ever seen with your naked eye, plus all the ones you have not, are just pieces of one larger thing. A galaxy. Our galaxy. The Milky Way. To understand how small Earth really is, we have to place our little sun inside that enormous structure and watch it shrink to nothing. The Milky Way is a spiral galaxy, a vast rotating disk of stars, gas and dust. Estimates vary, but it contains somewhere between 100 billion and 400 billion stars. Imagine standing in the middle of a city at night, surrounded by lights in every direction. Now stretch that city until it is 100,000 light years across. That is roughly the diameter of the Milky Way. From one edge to the other, even a beam of light would need 100,000 years to cross it. Where are we in this city of stars, not downtown? Our Sun sits about 26,000 light years from the galactic centre, in a minor spiral feature called the Orion Spur. It is not one of the grand main arms that wrap around the galaxy like glowing ribbons. It is more like a side street between two big avenues, the Sagittarius arm and the Perseus arm. We live in the galactic suburbs, far from the crowded central districts. At this scale, the entire solar system collapses into something almost impossibly small. If you built a model where the Milky Way was 100 feet across, our whole solar system would be thinner than a human hair. Not just Earth. Every planet, every comet, every orbit, the entire bubble of influence of our Sun would be a microscopic smudge inside a vast, flat disk. Earth itself would be so far below the resolution of the model that calling it an atom would still be generous. The Milky Way is not a simple pinwheel, though. At its centre lies the galactic bulge, a swollen sphere of stars about 10,000 light-years across. The stars there are old and packed far more densely than in our neighbourhood. If you lived on a planet near the centre, your night sky would never truly be dark. Thousands of stars would blaze overhead, some as bright as Venus appears from Earth, turning the night into a permanent cosmic twilight. Hidden inside that crowded region is the galaxy's dark heart, a supermassive black hole called Sagittarius A star. It has a mass of about 4 million times the mass of the Sun. All that mass is packed into a region only about 17 times the diameter of the Sun. That is hard to visualize. Take millions of stars worth of material, crush it down until its edge would fit comfortably inside the orbit of Mercury, and you have something like this object. We cannot see Sagittarius A star directly in visible light, but we can watch what it does to its surroundings. Nearby stars whip around it on tight, fast orbits. One star named S2 loops around the black hole once every 16 years, reaching speeds of about 5% of the speed of light at closest approach. At that moment, it is travelling faster than any human-made spacecraft has ever gone, just to avoid falling in. Gas clouds spiral toward the centre, heating up and glowing in infrared and radio waves as they approach their doom. For now, Sagittarius A star is relatively quiet. It does not have a bright disk of infalling matter. It is not spewing out enormous jets of energy like the most extreme black holes in other galaxies. But it has not always been so calm. Evidence shows that a few million years ago it was much more active. Astronomers have found giant bubbles of energy extending above and below the plane of the Milky Way, fossils of past outbursts from the central black hole. On long time scales, even the heart of a galaxy has moods. Moving outward from the centre, we meet the spiral arms. These are not solid structures carved into the galaxy. They are more like traffic jams in a rotating flow of stars and gas. Where an arm passes through, gas clouds get compressed and collapse, forming new stars. That is why spiral arms look bright in photographs. They are full of hot, young, massive stars that burn blue and fierce for only a few million years before exploding as supernovae. Those short-lived stars never move far from where they were born, so the arms stay outlined in their light. Our Sun is older and more ordinary. It has had time to drift away from its birthplace. Today we sit between major arms in a relatively quiet patch of disk. away from the worst of the supernova storms and high-energy radiation. That may not be an accident in the story of life. Violent star-forming regions can be dangerous neighborhoods. Being tucked into a calmer lane may have given Earth the stable, low-drama conditions needed for complex organisms to evolve slowly over billions of years. Beyond the bright disk lies the halo. This is a roughly spherical region surrounding the galaxy, extending to around 130,000 light-years from the center. The halo is home to old, metal-poor stars and to globular clusters, which are dense swarms of hundreds of thousands, or millions of stars packed into balls. A globular cluster like M13 contains so many stars in such a small volume that if you lived in its heart, your night sky would be crowded with brilliant suns in every direction. Compared to that, our quiet sky, with a few thousand visible stars, feels almost empty. The halo also hides something we cannot see at all: dark matter. We know it is there because of gravity. When astronomers measure how fast stars orbit around the galaxy, the outer stars move too quickly to be held in place by the gravity of the visible matter alone. There must be extra mass extending far beyond the bright disk. The best explanation is a vast halo of invisible matter that interacts mainly through gravity. This dark matter halo may stretch out to several 100,000 light-years and contain most of the Milky Way's mass. The stars, gas, planets, and you're riding inside a much larger, mostly unseen structure. The Milky Way is not alone either. Dozens of smaller satellite galaxies orbit it, like little boats circling a massive ship. The Large Magellanic Cloud and the Small Magellanic Cloud are the most famous, visible from the southern hemisphere as faint, fuzzy smears of light. Many others are faint dwarf galaxies with only a few million stars. Over billions of years, some of these satellites will be torn apart and absorbed, their stars added to the halos and streams that thread the larger galaxy. Big galaxies grow by eating smaller ones. The Milky Way has done this in the past and will keep doing it in the future. All of this structure, all of these motions and mergers and hidden halos, exist on a scale where the concept of Earth stops being useful. Our planet is 8,000 miles wide. The galaxy is 100,000 light-years across. The ratio between those sizes is so extreme that Earth does not just become invisible at this level, it becomes meaningless. You could erase our planet from the Milky Way and the galaxy's mass. Brightness and dynamics would not change in any way we could measure. Yet here is the paradox. From this unimaginable city of stars, on one anonymous arm of one ordinary galaxy, a tiny rocky world has spawned beings capable of mapping the entire structure. Orders of magnitude up in size, Earth is nothing. But from Earth, the Milky Way has become a knowable thing. In the next part, we will head even farther out, beyond our home galaxy into the vast neighborhoods of galaxies, clusters and superclusters, and finally into the filaments and voids of the cosmic web. At that scale, even a galaxy like the Milky Way starts to feel small. Inside the Milky Way, things already felt staggeringly large. Hundreds of billions of stars, a disk 100,000 light-years wide, a dark halo stretching even farther. It is tempting to stop there and call it the whole story, but the galaxy you live in is not the universe. It is just one island in a far bigger archipelago. To shrink Earth even further, we have to leave the island and climb high enough to see the entire chain. The first step out is called the local group. This is our immediate galactic neighborhood, a small cluster of galaxies held together by their mutual gravity. The local group spans roughly 10 million light-years from end to end. At its heart sit three main galaxies: the Milky Way, Andromeda, also known as M31, and the smaller Triangulum galaxy, M33. Around them swarm dozens of dwarf galaxies, each one containing only a few million or a few billion stars. In this setting, the Milky Way is big but not unique. Andromeda is even more massive, with perhaps twice as many stars. Triangulum is smaller but still a respectable spiral galaxy. The rest are tiny companions, many of them in the process of being stretched and torn by the gravity of their larger neighbours. Over billions of years, some of those dwarfs will be shredded into long streams of stars and absorbed, adding to the halos and disks of the bigger galaxies. Growth by cannibalism is normal on this scale. The local group itself is not static. The Milky Way and Andromeda are moving toward each other at hundreds of kilometers per second. In about 4.5 billion years, the two galaxies will collide and merge into a single larger system. It will not be a crash in the way your instincts imagine. The stars are so far apart that almost none will hit each other directly. Instead, their orbits will be scrambled, gas clouds will collide and trigger new star formation, and over time a new, more massive galaxy will take shape. By then, the Sun will be approaching the end of its life. Earth may be long uninhabitable or even gone. Even this future collision is a local drama. The local group is just one small collection embedded in something larger called the Virgo supercluster. Here the scales begin to twist your sense of size again. The Virgo supercluster spans roughly 110 million light-years across. It contains at least 100 galaxy groups and clusters. The local group, which already felt like a big deal, is one small node in this web. Near the center of the Virgo supercluster sits the Virgo cluster itself, about 54 million light-years away. The Virgo cluster hosts between 1,200 and 2,000 galaxies, many of them large spirals and giant ellipticals. One of the most impressive is M87, a massive elliptical galaxy with about 1 trillion stars and a central black hole billions of times the Sun's mass. Where the Milky Way once felt like an enormous city of stars, M87 is a sprawling metropolis, and the Virgo cluster is an entire country of galaxies. For a long time, astronomers thought in terms of superclusters like Virgo as separate structures scattered through space. Then, in 2014, something surprising emerged from detailed maps of galaxy motions. Researchers discovered that the Virgo supercluster was just a small part of an even larger flow of matter, a region they named Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a supercluster of superclusters. It stretches about 520 million light-years across and contains on the order of 100,000 galaxies. To define it, astronomers looked at how galaxies move, not just where they happen to be. They found that within this huge region, galaxies are slowly drifting toward the same general gravitational basin. The Milky Way, Andromeda, the Virgo cluster, all of them are like leaves caught in converging currents on the surface of a vast cosmic river. The center of this flow has been called the Great Attractor. For decades, we knew it was there because of the way it tugged on galaxies, but our own Milky Way blocked much of the view with its dust and stars. As different telescopes peered through in radio, infrared, and X-ray light, a picture emerged. The Great Attractor is not one single object. It is a region packed with massive clusters, including the Norma cluster, whose combined gravity pulls entire galaxy groups slowly inward. Even that is not the end of the story. Farther away, around 650 million light-years from us, lies the Shapley supercluster, an enormous concentration of galaxy clusters with a total mass equivalent to many tens of thousands of Milky Ways. It appears that Laniakea itself, along with the Great Attractor region, is being pulled toward Shapley. Everything we have mentioned so far, every galaxy and cluster, is participating in this slow cosmic drift down the slopes of gravitational hills that stretch for hundreds of millions of light-years. At this point, the Milky Way has become a statistical entry rather than a character. On the scale of Laniakea and beyond, it is one of 100,000 galaxies, a single bright dot in a smudged watercolor of light. Earth, 8,000 miles wide, orbiting one ordinary star on one quiet arm, is smaller than anything this map can meaningfully include. If we zoom out again, we start to see a pattern in how matter is arranged on the larger scales. Galaxies do not scatter randomly like sand blown across a floor. They cluster along long, thin filaments and dense nodes, leaving vast empty regions in between. This is the cosmic web. If you could step outside the observable universe and look back, the distribution of matter would look like a three-dimensional sponge or a network of glowing threads surrounding dark cavities. Within this web are enormous features with names that sound almost like myths. The Sloan Great Wall is one of them, a massive wall-like arrangement of galaxies discovered in 2003. It stretches about 1.37 billion light-years from end to end. That is billion, not million. Another monster is the Hercules Corona Borealis Great Wall. which may be the largest single structure ever found. Its length has been estimated at around 10 billion light-years, roughly 70% of the radius of the observable universe. When features reach that size, they start to test our understanding of how quickly structures can grow in a universe that has only had 13.8 billion years to evolve. Between the bright filaments and walls lie cosmic voids. These are regions where the density of galaxies is far lower than average. The largest known void, sometimes called the KBC void, after the initials of the astronomers who described it, is around 2 billion light-years across. That is a region so large that light would need 2 billion years to cross it, and yet it contains relatively few galaxies compared to its surroundings. If you could somehow place yourself in the middle of such a void and look out, the universe would feel much emptier. The nearest rich clusters would sit unimaginably far away, small knots of light on the horizon of your visible universe. The fact that we live in a region with a fairly typical density of galaxies is just that, a fact, not a guarantee. Most of the volume of the universe is in voids. The bright lattice of filaments and clusters occupies only a small fraction of the total space. All of this structure exists inside a larger boundary, the observable universe. This is not a physical edge with a sign saying stop. It is simply the limit of what light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. In that time, space itself has expanded while light was on the move. When you account for that, the region from which light can have reached us by now is a sphere about 93 billion light-years in diameter. Within that observable bubble, astronomers estimate there are roughly 2 trillion galaxies. Each of those galaxies can contain millions, billions, or even trillions of stars. A commonly quoted estimate for the total number of stars is around 200 billion trillion. That is 2 followed by 23 zeros. If every star were a grain of sand, you would need multiple Olympic-sized swimming pools to hold them all. On this scale, the Milky Way is just one of 2 trillion galaxies. In our earlier city analogy, where the Milky Way was a sprawling city of stars, the observable universe is an entire planet covered in cities, continents, and oceans of light. The local group becomes a small town, the Virgo cluster a county, Laniakea a province, and Earth drops below any mapping resolution. To get a hint of the ratios involved, imagine shrinking the observable universe down until it is the size of Earth. On that scale, the Milky Way would be smaller than a single atom. Earth would be much smaller than the particles that make up that atom. You could probe and never find it. It would not just be invisible, it would be physically meaningless at that level of zoom. Yet here we are, on that immeasurably small world, having this conversation about structures hundreds of millions and billions of light-years across. That is the quiet miracle hiding under all these terrifying numbers. A planet that does not even register on the largest cosmic maps has produced brains that can build those maps and argue about them. In the next part, we're going to flip the direction of our zoom, dive inward instead of outward, and see how the same universe that makes Earth negligible on large scales also makes it a giant on small ones. We will explore atoms, empty space, and deep time, and watch the meaning of scale invert all over again. We have climbed to the largest scales the universe offers, and watched Earth fade until it no longer made sense to talk about it. To balance that vertigo, let us now fall inward, because the same universe that makes Earth microscopic compared to galaxy clusters makes it unimaginably huge compared to the building blocks it is made from. When you zoom down far enough, our small planet turns into a towering giant. Start with the obvious. Earth feels solid. Rock under your feet, metal in your hands, oceans you can drown in. It does not feel like something that could be made of tiny, mostly empty things. Yet everything on and in Earth is made of atoms. The simplest atom, hydrogen, has a diameter of roughly 1/10 of a billionth of a meter. That is so small that you could line up about 10 million hydrogen atoms across the width of a single human hair. Earth itself has a mass of about 6 trillion kilograms. Most of that is iron, oxygen, silicon, magnesium, and a collection of other elements. If you take those elements and break them down into individual atoms, You end up with a number so large it almost stops being a number. Roughly speaking, Earth contains something like a 1 followed by around 50 zeros atoms. If you tried to count them at a rate of 1 atom per second, you would not finish in the current age of the universe, not even close. Each of those atoms has structure of its own. At the center sits a nucleus made of protons and neutrons. Around that nucleus is a cloud of electrons. When you picture that cloud as a kind of fuzzy shell, it is easy to assume the atom is tightly packed. It is not. The nucleus is tiny compared to the atom. If an atom were scaled up to the size of a football stadium, the nucleus would be like a marble at the center of the field, and the electrons would be whisper-thin layers far away toward the stands. Everything in between would be empty space. Despite being so small, the nucleus carries almost all the mass. Protons and neutrons are about 1,800 times more massive than electrons. Electrons occupy almost all the volume, but contribute almost nothing to the weight. The heavy stuff, the part that actually resists acceleration, is crammed into that marble at the center. Dig deeper, and the story continues. Protons and neutrons can be broken down into even smaller pieces called quarks. As far as we currently know, quarks are fundamental. They are not made of anything smaller. At that level, our language starts to fail. We talk about quantum fields and probability patterns rather than little balls of stuff. The solid world you experience is really a complicated dance of these fields, with forces holding everything in place. The important takeaway is this: Earth, the thing that seems so dense and solid, is mostly empty when viewed at atomic scale. If you could somehow remove all the empty space inside atoms and push all the nuclei together until they were touching, you would get something mind-bending. Compressed to nuclear density, all the matter in Earth would fit into a sphere only a few hundred feet across. Imagine a large skyscraper, and you have the rough size. You're not mishearing that. A planet 8,000 miles wide could, in principle, be squeezed down to something you could walk around in an afternoon. This is the same kind of density you find in neutron stars, those city-sized remnants of massive stars that pack more mass than the Sun into a ball only a dozen miles across. It is an extreme reminder that scale is not just about length. It is about how much stuff you cram into that length. At nuclear densities, Earth would be tiny. At human densities, it is huge. Scale is not only about size and space, though, it is also about time. So let us hold our compressed Earth in one hand and stretch the timeline of its life out with the other. Earth formed about 4.5 billion years ago from a swirling disk of gas and dust around the young Sun. The early planet was molten, hammered by impacts. Over time, it cooled enough for a crust to form, oceans to condense, and an atmosphere to thicken. Life showed up surprisingly quickly once conditions settled. The oldest evidence we have of life is around 3.8 billion years old. For billions of years after that, Earth was a world of simple, single-celled organisms. No trees, no animals, no flowers, just microbial mats, films, and tiny cells drifting in ancient seas. Complex multicellular life, the kind that gives you animals and plants, did not really take off until about 600 million years ago. Then came the Cambrian explosion around 540 million years ago, a burst of evolutionary innovation that filled the oceans with a wide variety of body plans. Since then, life has gone through booms and crashes, mass extinctions and recoveries, continents splitting and rejoining. To make the timeline more human-sized, imagine Earth's entire history compressed into a single year. Earth forms on January 1st. Life appears in March. For most of the year, only simple life exists. The Cambrian explosion does not arrive until mid-November. Dinosaurs show up in December. They go extinct around December 26th. Humans appear in the last minutes of December 31st. All of recorded human history fits into the final 10 seconds before midnight. Everything you think of as history happens in a breath at the end of the year. Now compare that year to the age of the universe itself. The universe is about 13.8 billion years old. Earth formed after roughly 9.3 billion of those years had already passed. That means our planet has existed for about 1/3 of cosmic history so far. Long before Earth, stars were being born and dying, Galaxies were colliding, elements heavier than hydrogen and helium were being forged in stellar cores and supernova explosions. Looking forward, the timeline gets even stranger. Evidence suggests the universe will keep expanding indefinitely. Star formation will continue for trillions of years, gradually slowing as galaxies use up or lose their gas. At some point in the far future, around 100 trillion years from now, star birth will effectively end. The universe will enter what is sometimes called the degenerate era, dominated by long-lived red dwarfs, white dwarfs, neutron stars and black holes. Even that is just a chapter. Over unimaginably longer stretches, white dwarfs will cool and fade. Stellar remnants will collide, evaporate, or be swallowed by black holes. Black holes themselves are not eternal. Through a process called Hawking radiation, they slowly leak energy. A supermassive black hole like the one at the Milky Way center could take roughly a 1 followed by 100 zeros years to evaporate completely. That number is so vast it stops feeling like time and starts feeling like an abstract label. Against that backdrop, Earth's 4.5 billion years are a brief spark. Its future as a habitable world is shorter still. In about 1 billion years, the gradually brightening sun will likely make Earth too hot for complex life as we know it. In about 5 billion years, the sun will swell into a red giant, possibly engulfing the inner planets or stripping Earth to a dead, scorched core. Eventually, the sun will shrink into a white dwarf, and Earth, if it survives, will become a frozen relic circling a dim ember. Seen from the outside, Earth is a short-lived, medium-sized, rocky planet in a universe that will outlast it by factors that embarrass language. Seen from the inside, down at the scale of atoms and up through the scale of human days and years, Earth is unfathomably rich and vast. Both perspectives are true, both matter. In the next part, we will look at how humans slowly discovered these truths, step by reluctant step, and how every advance in our understanding pushed Earth further from the center of the story it once occupied. For most of human history, none of the cosmic numbers you have heard in this video existed. There were no light years, no galaxies, no superclusters, not even a solar system in the modern sense. There was only the sky, a moving dome of lights above a solid, unmoving Earth. The story of how we escaped that picture is not just a list of discoveries. It is a series of ego hits. Each one shoved us farther from the center we thought we occupied. Imagine yourself as an ancient observer with no telescope, only your eyes. Every day the sun rises in the east and sets in the west. Every month the moon waxes and wanes and drifts among the stars. The constellations rotate overhead at night like a painted ceiling. Nothing in that experience shouts that Earth is spinning and circling a star. The obvious explanation is that Earth is fixed and everything else moves around it. Greek philosophers like Aristotle built an entire model on that intuition. Earth sat at the center, heavy and motionless. Around it, the heavens were arranged in perfect crystalline spheres that carried the moon, the sun, the planets, and the distant stars. The outermost sphere held the fixed stars. The inner spheres swept the wandering planets along paths that tried to match their odd, backward loops across the sky. Everything beyond Earth was supposed to be perfect and unchanging, made of a special heavenly substance. It was a comforting architecture. There was one problem. The planets did not cooperate. Mars in particular would move forward against the background stars, then slow down, then reverse direction for a while, then resume its march. To explain this without giving up the central Earth, later thinkers like Ptolemy introduced a system of circles on circles. Planets moved in small circles called epicycles, whose centers moved along larger circles around Earth. With enough loops and tweaks, the model could be made to match observations reasonably well. It worked on paper, and it kept Earth at the center, which made sense to cultures that believed the cosmos had been designed for us. This geocentric universe lasted for almost 2,000 years. It was not just a scientific theory, it was woven into religious and philosophical ideas about human importance. To say that Earth was not at the center was not just a technical correction. It was a threat to an entire worldview. That is why the next shift hurt. In the 16th century, Nicholas Copernicus proposed something radical. He suggested that the sun, not Earth, sat at the centre of the known planetary system. Earth, he argued, was one planet among several that orbit the Sun. The strange backward motion of Mars was not Mars doing loops around an unmoving Earth. It was a perspective trick that happens when a faster inner planet overtakes a slower outer one. The heliocentric model suddenly made the planetary dance much simpler. Copernicus still imagined perfect circles and added his own smaller corrections, so his version was not immediately more accurate than the old one. But it had a deeper elegance. Planets no longer needed elaborate epicycles just to explain their basic motion. Most people did not read his book, and those who did faced a choice: accept the new model and admit that Earth was not at the centre, or cling to the old picture that matched scripture and intuition. Many chose the second path. Then Galileo Galilei pointed a new tool at the sky. In the early 1700s, he built and refined one of the first telescopes and aimed it at the Moon, the Sun, and the planets. The Moon, which had been assumed to be a perfect smooth sphere, turned out to have mountains and craters, scars and shadows. The Sun showed dark sunspots that changed over time. Perfection had cracks. Most importantly, Galileo discovered 4 small points of light near Jupiter that changed position night after night. They were not fixed stars, they were moons orbiting Jupiter. This was a direct visual demonstration that not everything circled Earth. He also observed the phases of Venus, which matched the predictions of a heliocentric system and did not fit the geocentric one. The evidence for a sun-centered model was suddenly visible to anyone with a telescope and an open mind. The response was not enthusiastic. Galileo was tried by the Inquisition and forced to publicly recant his support for a moving Earth. He spent the rest of his life under house arrest. Officially, the theory was suppressed, but the observations could not be unseen. Other astronomers confirmed and extended them. The idea that Earth orbits the Sun slowly pushed its way from heresy to fact. Johannes Kepler tightened the model by showing that planetary orbits are not perfect circles. They are ellipses, slightly stretched loops with the Sun at one focus. This small change made the predictions match reality with remarkable precision. Isaac Newton later explained why those ellipses exist at all, by formulating the law of universal gravitation. The same gravity that makes an apple fall pulls planets into their orbits and keeps the Moon circling Earth. The heavens and Earth followed the same rules. By the 18th century, Earth was no longer at the centre of the solar system. We were one planet among several. For a while, people could still hope the Sun itself sat at the centre of the universe. That comfort did not last either. In the early 20th century, Harlow Shapley studied globular clusters, the dense balls of ancient stars scattered around the Milky Way. By mapping their positions, he found that they were not centered on the Sun. They were centered on a point far away in the direction of the constellation Sagittarius. From this, Shapley concluded that the Milky Way was much larger than people had thought, and that the Sun was located in its outer regions, not at its center. Our solar system moved from the middle of everything to the outskirts of a single galaxy. The pattern was repeating. Each new measurement pushed us farther out. Then came perhaps the most humbling discovery of all. In the 1920s, Edwin Hubble used the largest telescopes of his time to study faint fuzzy patches of light in the sky called nebulae. Some believed these were small clouds inside the Milky Way. Hubble identified individual variable stars in one of them, the Andromeda Nebula, and used their brightness to estimate its distance. The answer was shocking. Andromeda was far outside the Milky Way. It was not a cloud within our galaxy. It was a separate galaxy entirely. Suddenly, the Milky Way shrank from the universe to one galaxy among many. As more observations came in, it became clear that the sky was filled with galaxies at various distances. Hubble also discovered that nearly all of them were moving away from us, and that the farther away a galaxy was, the faster it seemed to recede. This relationship pointed to an expanding universe with no special center. Space itself was stretching, carrying galaxies with it. From that pattern grew the idea of the Big Bang, a universe that began in a hot, dense state, and has been expanding and cooling ever since. In that picture, no place is truly at the center. Every galaxy sees other galaxies speeding away, just as every point on the surface of an inflating balloon sees other points move away. Once again, the human desire to stand in the middle of things collided with the math and lost. The decentering did not stop there. In the late 20th and early 21st centuries, astronomers found planets around other stars by the thousands. Exoplanets came in every size and configuration. Gas giants hugging their stars, rocky worlds larger than Earth, small scorched spheres and icy distant orbits. Earth was no longer just one planet among 8 in the solar system. It became one world among billions of possible rocky planets in the Milky Way alone. At the same time, surveys mapped the distribution of galaxies on ever larger scales. They revealed the filaments, clusters, and voids of the cosmic web. They hinted at dark matter shaping the skeleton of that web and dark energy driving the acceleration of cosmic expansion. In every new map, Earth is barely a concept. The solar system is a dot. The Milky Way is a small smudge among many. Step back and you can see the pattern. Our ancestors placed Earth at the center of a small, cozy cosmos and saw that as proof of our importance. Over centuries, observation after observation pushed us away from the center of everything. First we lost the middle of the solar system, then the center of the galaxy, then the role of unique galaxy, and finally any claim to a privileged position in the universe at all. On paper, this should make us feel insignificant. In practice, it does something stranger. It replaces comforting illusion with a deeper kind of wonder. The fact that we are not at the center, that we orbit an ordinary star in an ordinary galaxy in no special place, makes the existence of conscious life here more remarkable, not less. In the next part, we're going to look directly at that tension. In a universe where we are so clearly not central, why does life on this tiny world still feel so important? And what does the silence from the rest of the cosmos really mean? By now the picture is clear. We live on a tiny world that barely registers on any cosmic map. We orbit an ordinary star in a suburban arm of an ordinary galaxy that is one of trillions. The universe is ancient, vast, and full of stars and planets. That leads to a question that is almost impossible to ignore. If the cosmos is so big and so old, where is everybody? This puzzle is often called the Fermi paradox. On one side, you have the raw numbers, hundreds of billions of stars in our galaxy alone, probably billions of Earth-sized planets in stable orbits, 2 trillion galaxies in the observable universe, each with its own horde of stars and worlds. On the other side, you have the evidence, which is nothing. No confirmed signals, no alien probes, no obvious megastructures blotting out starlight. The galaxy looks empty of technological life. One way to resolve that tension is brutal in its simplicity. Maybe intelligent life is rare, not planet rare. There are plenty of planets, not simple life rare. Microbes might arise wherever there is liquid water and energy. The rare part might be the combination of events that lead from chemistry to cells to complex bodies to brains that can build radios and rockets. That path on Earth took billions of years and involved a long chain of lucky breaks and near disasters. We only have one example to study. All life on Earth appears to share a common ancestor. Plants, animals, fungi, bacteria. You and every tree you have ever seen are branches on the same ancient family tree. That suggests that whatever happened to turn non-living chemistry into the first living system happened once and then spread. Was that step easy and inevitable on any wet, rocky world? Or was it a freak accident in one warm pool on one planet in one galaxy? We do not know. Even once life exists, climbing to complexity is not guaranteed. Single-celled organisms ruled Earth for around 3 billion years before multicellular life really took off. Intelligence of the humankind took even longer. For most of Earth's history, there were no animals planning for the future or building tools. It is entirely possible that the universe is filled with worlds where life appeared quickly, but never progressed beyond microbial mats and simple cells. Those worlds would be biologically rich, and yet permanently quiet on the radio. Another possibility is more unsettling. Maybe intelligent civilizations do arise fairly often, but they do not last. Technology gives a species power over its environment, but not automatic wisdom. A civilization that discovers nuclear energy can power cities. It can also destroy itself. A civilization that learns to burn fossil fuels can build an industrial world. It can also destabilize its climate. A civilization that creates advanced artificial systems can cure disease or lose control of its own tools. The same leaps that let a species reach the stars might also give it new ways to go extinct. In that picture, the galaxy could be littered with ruins. Civilizations might flare into existence, rearrange their corner of the cosmos for a short time, and then vanish long before anyone on another world notices. The silence we hear now could be the silence after many storms. If that is true, then the fact that we are still here, still able to ask these questions, is both lucky and extremely fragile. There are kinder answers as well. Perhaps advanced civilizations exist and simply choose not to announce themselves. They could be watching from a distance, following a kind of informal rule about avoiding contact with emerging species. Or they might be so different from us that they have no interest in conversation. Ants do not build radio telescopes to contact humans. They just keep doing ant things. On some higher level, we might be the ants. It is also possible that we have been looking in the wrong way at the wrong time. For a few decades, we have pointed radio dishes at a tiny fraction of the sky and listened in a few limited frequencies. Maybe other civilizations use methods we have not imagined yet. Maybe their communication periods are short compared to the ages of stars. Two species could send brief bursts of signals separated by millions of years and miss each other entirely. The galaxy could be full of short-lived conversations that never overlap. And then there is simple distance. Space is not just big. It is structured in a way that makes contact hard. Radio waves spread out and fade. Signals weaken with every light year. A beacon that is easy to detect nearby becomes a whisper against background noise farther away. Physical travel is even worse. With our current technology, reaching even the nearest stars would take tens of thousands of years. Even with optimistic future drives, starflight would demand lifetimes of commitment. The universe may host countless civilizations that are effectively isolated by the very scale we have been exploring. Whatever the explanation, practically speaking, we are alone right now. Not necessarily alone in the universe, but alone in the sense that there is no one else we can talk to, trade with, or ask for help. Every observation we can actually make still points to the same conclusion. Earth is the only confirmed world with life, and the only confirmed world with a technological civilization. Until we discover something different, we have to behave as though that uniqueness matters. This is where the story of smallness flips again. In terms of size, Earth is negligible. In terms of content, it might be extraordinary. It carries a biosphere that has been evolving for billions of years. Millions of species, each with its own history and adaptations, woven into a global web of relationships. Coral reefs, rainforests, deep-sea vents, birds, whales, microbes in the soil, all playing their part in maintaining a habitable world. That entire tapestry exists on a speck that does not even show up when we map galaxy clusters. On top of that biosphere sits something rarer still, self-aware minds capable of reflecting on their own existence. Right now, as you listen, your brain is processing photons that left screens and speakers a fraction of a second ago. Those patterns of light and sound are telling you a story about the universe from the scale of quarks to the scale of superclusters. Matter that once existed only as hydrogen in a young galaxy has reorganized itself into neurons that can understand fusion, gravity, dark matter, and cosmic expansion. That is not a small thing. If intelligent life is common, then the universe might be full of places where this kind of awareness blossoms. If intelligent life is rare, then it is possible that in a large region of space, maybe in the entire Milky Way, we are the only ones currently doing this. The only ones building telescopes, writing equations, making art, worrying about our future, and sending machines beyond our home world. The only ones handing knowledge from one generation to the next in a chain that stretches farther every century. In that case, what happens on Earth takes on a kind of quiet cosmic weight. The universe itself is not judging us. It is not giving us a mission. But through us, the universe has developed eyes and ears and instruments. It has learned to measure itself, to map its history, to predict its future. If we disappear, that local patch of awareness goes dark. The atoms remain, the stars keep burning, but the ability of this tiny corner of reality to understand itself might vanish for good. That thought does not need to make you anxious. It can make your daily choices feel oddly profound. Protecting ecosystems, reducing the risk of global catastrophes, building a stable civilization. All of that is not just about being nice to our descendants. It is about preserving something the cosmos seems to produce rarely, if at all, a network of minds capable of wonder. Looking ahead, we stand at an awkward moment. We are powerful enough to change the planet, but not yet wise enough to always do it carefully. We are capable of sending machines to other worlds, but not yet able to send ourselves safely to the stars. We are advanced enough to understand extinction, but still entangled in conflicts and habits that could push us toward it. The decisions we make over the next few centuries will shape whether life from Earth remains a brief flare on the cosmic timeline or becomes a long-lasting participant in the story of the universe. In the final part of this journey, we will bring all of these threads together. We will return from the farthest edges of the observable universe back down to this pale world and ask what it really means to live on a planet that is tiny beyond comprehension and yet may be uniquely precious. We will look at possible futures, from extinction to a galaxy-spanning civilization, and ask what kind of story we want to write from this point forward. We have now walked the entire ladder of scale, from the ground beneath your feet to the edge of the observable universe, and back down into the heart of atoms. Along the way, something kept repeating. Every time you zoomed out, Earth shrank. Every time you zoomed in, Earth turned out to be built from countless smaller parts. At no level of description did the universe stop and say, this is the size that matters, which means something important. Meaning was never hiding in size in the first place. Think about where we started. Earth felt enormous compared to you. You could spend a lifetime traveling and never see every desert, forest, and ocean. From that vantage point, the planet was a whole world, which is exactly the right word. Then you met the moon and saw the empty miles between the two. You met the sun and watched Earth collapse into a peppercorn held at arm's length. You stretched the solar system out across a football field and realized that almost everything in it was vacuum. Then the ladder kept going. The nearest stars turned the solar system into a single bright dot. The Milky Way turned those dots into anonymous lights in a sea of hundreds of billions. The local group, the Virgo cluster, the Laniakea supercluster, the cosmic web, the observable universe. At every step, Earth fell another level down in size and importance. By the time you reached the full map of what we can see, Earth was not just invisible. It was smaller than any reasonable analogy could capture. On that canvas, our world may as well not exist. And yet, zoom back down and Earth returns with a different kind of power. You see a world layered with oceans and continents, weather systems and seasons. You see a crust sliding around on a hot mantle, a metallic core generating a magnetic shield, cycles of carbon and water and rock that have kept the planet habitable for billions of years. You see a surface that once glowed red with lava, now covered in blue and green. Zoom in further and you find life everywhere. Microbes under Antarctic ice, worms at the bottom of the ocean, trees trading nutrients through fungal networks. Birds navigating by magnetic fields, your own body made of cells that are constantly repairing, replacing, and communicating. All of that complexity rides on a framework of atoms and molecules, dancing according to quantum rules that were set long before Earth formed. It took the entire history of the universe to set the stage for this particular planet to exist in this particular way. Then there is time. On geological scales, human history is not just short. It is almost absent. Yet within that short window, you belong to a species that has learned to read the universe. You have taken fossils and rocks and light from distant galaxies and turned them into a story stretching from the Big Bang to the present. You have discovered that the same physics that shapes galaxies also shapes your coffee cup. The same forces that bind quarks into protons bind you to the ground and keep Earth in orbit. From the universe's perspective, your existence is a brief flicker. From your perspective, that flicker is everything. So what do you do with this double vision? On one side, you're smaller than a thought in a cosmic mind that does not exist. On the other side, you are part of the only mind the cosmos has currently produced in this region of space. It is easy to slide toward despair and say nothing matters. It is just as easy to ignore the whole picture and live as if your corner is the only one that exists. The challenge is holding both truths at once. The first truth is humility. You're not at the center. Earth is not at the center. The solar system is not special. The Milky Way is one of trillions. Most of the universe will never know you are here. Your victories and failures will not tilt the cosmic web. When a galaxy cluster merges 1 billion light-years away, it will not pause to consider your feelings. That sounds harsh, but it is also freeing. The universe does not demand that you be important on its terms. It leaves you alone to define importance on yours. The second truth is responsibility. As far as we can tell, this small world contains the only confirmed life in the observable universe. It contains the only confirmed intelligence capable of mapping that universe and caring about what it finds. If you disappeared tomorrow, the expansion of space would continue. Supernovae would still explode. Black holes would still slowly leak energy. The physics would not notice. But locally, something vast would be lost. The ability of matter in this region to look back on itself and say, "I understand a little," would go dark. You do not have to carry that weight all the time. You do not have to wake up every morning and think my recycling habits are an act of cosmic stewardship. That is not sustainable. What you can do is let this perspective seep quietly into your choices. When you argue about borders, remember that every border you care about is a line drawn on a dust speck. When you watch news about conflicts, remember that both sides are made of stardust arranged into nervous systems that feel pain and joy just as you do. When you worry about the future, remember that the very fact you can worry is a rare property in a universe mostly filled with nuclear fire and cold vacuum. On the scale of galaxies, a kinder civilization and a cruel one look identical. The number of photons they emit is almost the same. The amount of mass they move around is almost the same. The difference exists entirely in the experiences of the beings inside. That is where meaning hides. Not out in galaxy clusters, but in the way conscious creatures treat each other on worlds too small to see. There is also room for hope here. If we can survive our own power long enough, we might carry Earth's story off Earth. We might build habitats on Mars, cities in space, stations orbiting distant moons. We might send slow-moving probes toward other stars that carry frozen seeds, or digital mines, or something we cannot yet imagine. In time, our descendants might spread across a significant fraction of the Milky Way, turning our current tiny footprint into a much larger presence. Even then, though, every new world would be another pale speck. Every colony would face its own challenges, its own chances to forget how small and precious its home is, or we might not make it. Civilizations are experiments, and experiments fail. If we destroy our biosphere or collapse in conflict or simply fail to adapt to a changing world, the universe will not punish us. It will just move on. Some other planet somewhere might pick up the thread millions or billions of years later. There is no guarantee that life on Earth is irreplaceable on cosmic scales. But from where we stand now, with no evidence of others, acting as though it is irreplaceable is the safest bet. Which brings us back to you. Right now, you're a person on a spinning ball of rock, listening to a voice that is trying to stretch your imagination across 93 billion light years and 14 billion years of time. Tomorrow you will still have bills, relationships, frustrations, and small joys. The universe will not simplify your life just because you understand it a bit better. What it can do is offer context. The next time you look up at the night sky, try this. First, see it the way your distant ancestors did, as a dome of lights above a solid world. Then gently overlay the real picture. Each point of light is a sun. Many have planets. Some of those planets may have oceans, mountains, and skies of their own. Your galaxy is one swirl of hundreds of billions of such stars, drifting in a web of filaments and voids. Somewhere out there, light is leaving a distant galaxy right now that will not reach any observers for millions of years. And then bring your attention back down to your feet, to the street or floor you are standing on, to the air you are breathing, to the heartbeat in your chest, everything you are is the product of a universe that has spent billions of years cooling, condensing, and experimenting with complexity. You're small in size, but you're large in context. Your life is fleeting, but it is happening during the one moment in this region of space when such lives are possible. If this journey changed how you feel about our planet even a little, do something simple to mark that. Take a breath and feel grateful that you get to be a conscious part of this story at all. And if you would like to keep exploring big questions about space, time, and our place in the cosmos together, consider liking this video and subscribing to the channel. It really does help me keep making these long, deep dives. For now, as you close your eyes tonight, remember this: the universe is enormous, Earth is tiny, but Earth is also home to life, to awareness, to you. That combination might be rare beyond anything we can currently imagine, which makes this small world, and the brief time you get to spend on it, something worth protecting and something worth celebrating.